In section 11.7, we're going to talk about modeling real-world data with exponential and logarithmic functions. Just like we modeled real-world data with linear, quadratic, cubic, and quartic functions, we're also going to learn how to model the real-world data with exponential and logarithmic functions. There is a function in the StatCalc menu that is an exponential regression, and that's what we're going to talk about today. So first, let's talk about doubling time. Doubling time is the amount of time t required for a quantity modeled by the exponential equation n equals n naught e to the kt to double given by the following equation. T is equal to the natural log of 2 divided by k. Now, where that comes from, we had talked about the amount of time that it takes to double something. Well, if the initial amount is 1, when you double it, you have 2. Well, that 1 becomes negligible. You don't really need it there. And in order to solve this exponential equation, you would take the natural log of 2, and that would make e go away from the right-hand side. And then you would divide by k. And that's where the equation for doubling time comes from. In example 1, it says Hosea, a senior at Allen East High School, has saved $2,000 from his summer job mowing lawns. He would like to invest the money so that he would have double the money in 6 years when he graduates from college. Hosea invests the $2,000 in an account that pays 8% interest compounded continuously. Will Hosea have doubled his money in 6 years? Explain. So, let's find out. So, t is going to equal the natural log of 2 divided by k. Well, k is like your interest rate. So, we're going to write 8% as 0.08. The natural log of 2 divided by 0.08 is about 8.66. So, it's going to take 8.66 years to double his money, which means he will not have doubled it in 6 years. In part B, it says what interest rate is required for an investment with continuously compounded interest to double in 6 years. So what if I do want it to double in 6 years, and I want to know what the interest rate is going to be? This time we're going to solve for k. Remember, this is just a proportion. So I'm going to get 6k is equal to the natural log of 2. So k is going to be the natural log of 2 divided by 6. And the natural log of 2 divided by 6 is going to be approximately 0.116, which is about 11.6% interest if he wants to, if he wants to double his money in 6 years. So we've talked about scatter plots and determining what kind of a regression is modeled by our scatter plot. But like I said, so far we've only talked about linear, quadratic, cubic, and quartic. Well, sometimes our scatter plot displays exponential growth or decay or logarithmic growth or decay. So these are two examples. This is your exponential decay on the left and exponential growth on the right. So if you get a scatter plot that sort of looks like that, it's going to be exponential growth or decay. Remember that the graphs of the logarithms were the inverses of the exponential graphs. And these are your logarithmic graphs, where the one on the left is growth and the one on the right is decay. But how are you going to know which one's which? Like, how do you know which one to use? Well, if it appears that there is a horizontal asymptote, it's probably exponential growth or decay. And if it looks like there's a vertical asymptote, it's probably a logarithmic growth or decay. Let's do an example of an exponential scatter plot on the calculator. It says India is expected to have the largest population in the world by 2050. The table below gives the population of India in 100 millions for selected years between or during the 1900s. Remember that when we do these regressions, we don't like to actually plug in a year for list 1. We usually like to do years since something. So we're going to do years since 1950, so that's why 1950 is 0, 1960 is 10, and then 20, 30, 40. This is going to be our input, and that'll go into list 1, and this will be my output, and it'll go into list 2. Remember that you find the lists by going into Stat, number 1, Edit. If you need to clear out your data, if you already have data in list 1 and list 2, then you're going to put the cursor on L1, and then you're going to press clear, which is on the right-hand side, and then the down arrow. If you press delete instead of clear, it'll delete the list. It's easy to get back. You just go to Stat, number 5, enter, and that'll fix the problem. So clear out your lists and put in 0, 10, 20, 30, 40 in list 1, and 3.58, 4.42, 5.55, 6.89, and 8.51 into list 2. And it should look like this. After you have the data in, we're going to determine, is this exponential growth or decay or logarithmic growth or decay? It really doesn't matter if it's growth or decay, because the calculator will write the equation for you. But in order to look at the stat plot, you need to go to second, y equals, and turn the first stat plot on. So number 1, hit enter, and then put the cursor on, and then hit enter. So it'll turn the stat plot on. Once it's on, you don't have to turn it off again unless the calculator won't graph for you. But for now, just leave it on, and then press zoom, number 9. That's your zoom stat. And you should get this graph. So, because it looks like the graph is doing this, we're going to go with it being exponential growth. So now to write the equation, you're going to go back into Stat, but this time you're going to go to Calc, and I want you to find exponential regression. It's probably option 0, and it says EXPREG. And then hit enter, probably twice until the equation pops up. The equation is going to be in the form y equals a times b to the x, because this is an exponential equation. So the equation is going to be y equals about 3.5758, I'm just rounding it to 4 decimal places, times 1.02, I guess it's going to round it to 0 to the x. Now that we have the equation, part B said use the equation to predict the population of India in 2050. First of all, remember that x is the number of years since 1950. So x is going to be 100. And also remember that the answer is in 100 millions. So now, for part B, we're going to plug in 100 for x and plug this into the calculator. And I'm going to get about 31.5. And remember that's in 100 millions, which means you have to multiply that by 100 million to get the actual answer. Well, 100 million is going to be, let's see, a million is 6 zeros, so 10 million is 7 zeros, so 100 million must be 8 zeros. So we need to move the decimal 8 spaces to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Well, that turns out to be 3,150,000,000 people, approximately by 2050. If you do a search of world populations, you will find that India is one of the fastest growing countries in terms of its population. It's about to, if it has not already, surpassed China. We're going to do one more, and I'm going to also show you how to change this exponential equation that the calculator writes into an exponential equation in terms of e, because the calculator doesn't write it for you in terms of e. So, the number of bacteria in a culture is observed for several hours with the following result recorded. Find an equation that models the data. So first we're going to put the data into the calculator. This is going to go in list 1, this is going to go in list 2. Once your data's in, you've already turned your stat plot on, so you can just go to Zoom 9 to do the graph, and this is what you should get. It's a little choppy, but it's probably exponential growth. So then you go back into Stat Calc and find exponential regression and write the equation. And the equation is going to be, so now I gotta go back and do this again. My exponential regression appears to be y equals 6.5828 times 1.1769 to the x. Now what we're going to do is we're going to go back and we're going to rewrite this in terms of base e. Because the calculator doesn't do it for you, we need a little mathematical manipulation to do this. So remember that e and ln are inverses of each other. So if you have something like e raised to the natural log of 2, the answer is 2. If you have the natural log of e squared, the answer is 2, because every time these cancel each other. We're going to use that fact to rewrite this. So what I'm going to do is I'm going to take what's inside the parentheses and I'm going to rewrite it as e to the natural log of 1.1769. The reason that I can do that is because remember that e and ln cancel, so I haven't really changed the equation, even though it kind of looks a little different. Now I'm actually going to evaluate the natural log of 1.1769. 1.1769, and my calculator spits out, let's see, 5828, e to the 0.1629, and then there's an x. So this is the same equation, except in terms of base e. And the way that I did it was I took what was inside the parentheses from the regression, the exponential regression function on the calculator, and I did e raised to the natural log of that number. And then I took the natural log of that number. And that is modeling real-world data with exponential and logarithmic functions.